Yeah.
All right. You can ask a question.
Yeah, so I was hoping to go over the process for solving a question with like a pulley and a weight. I don't have like a specific question in mind, but I was going back to the lecture slides. And I just was like a little bit confused how to like actually solve it.
Can you see the screen?
No, it's blurry.
Blurry. All right. It should go to focus now. Can you see it?
No.
Still blurry?
Yeah.
Now?
Oh, that's better.
Can you see the picture?
It just got blurry again.
Oh shit! All right.
That's better.
No, it's not you. It's Zoom. You should see it now.
Yeah.
All right. So, do you have a specific question?
Well, I was looking back the lecture slides, and it was just like solve for the tension in the like string. And when I tried to solve it, I just was confused. I like couldn't quite follow the solution on like in the slides.
All right. So we see two objects here. Number one, number two. That means we should analyze the motion of each object individually first, and then we can figure out some connection between those. For example, for a disk, we only have one important force. Well, it could be, like in our example, attached to some stand, but it doesn't matter because this force of gravity and this normal force, they not responsible for rotational motion, because naturally we can choose the axis of rotation in the middle. So there is no torque for gravity, there is no torque for normal, there's only torque due to tension.
Yeah.
And the magnitude of this torque equals tension times the radius, in this case. So this is the object. We have to write a law, and by now we know many different laws. So we have to choose what law do we want to write. We have law of conservation of mechanical energy, the law of conservation of linear momentum, the law of conservation of angular momentum, Newton's first law, Newton's second law, Newton's third law. So which do you want to use?
The Newton's second law for angular momentum.
Newton's second law applies for rotational motion. Exactly. So you see, and well, you made the choice. Now you write it down. Net torque equals moment of inertia times angular acceleration, and in this case, well, I could write magnitudes if I want to There's only one torque responsible for angular acceleration. I could use components, or the problem is that the components should be written relative to z-axis, the axis that points out of the screen, so it's hard to see it. But we also have clues. They say everything clockwise is negative, and in this case, components for both are negative. But of course, if you multiply by -1, you get exactly the same equation again. So, and the inertia equals given expression because it's a disk.
Mm-hmm.
That's basically it for the object number 1. Now we have to move on to the object number 2. And now we've got to do the same reasoning. What law? Well, obviously, now it's Newton's second law for translational motion. And this is a tension, which kind of not exactly the same, but has the same magnitude.
Mm-hmm.
Because the string is ideal. And it will travel with a given acceleration, or I don't know, unknown acceleration. I don't know. Doesn't matter. Now, if we write the law, we got one positive component, one negative component, and another negative component. And that's it. So we got equations 1 and 2, plus some additional, less important equations. We know the magnitude of the tension is the same. Now, the only thing we need to relate is these variables, acceleration and angular acceleration. Those different variables are different, but must be related. And for that, we again use the fact that the string does not stretch, so it's an ideal string. So for example, if this weight travels down by, I don't know, 1 centimeter, certain distance, so the string unwinds, and if we take a look at any point at the rim, at the edge of the wheel, it will travel the same distance. This is the connection. So this motion is coupled, and distance over the radius equals the angle traveled by this point. Theta. But if the disk spins faster and faster, the angle changes. So it gives us two more variables, angular velocity and then angular acceleration. But the good thing about it, if we divide here on radius here, oh no, here I want to multiply. So distance equals theta times radius. So I want to multiply by the radius here and here, by the radius here and here. And this transition tells us, well, this eventually is related to how fast speed changes, and that is the acceleration of this point, the linear acceleration of this point, and it has to be equal to angular acceleration of this wheel times radius, but it also this is equal to the same acceleration because it travels the same distance at the same time. It has the same speed as this dot, same acceleration as this dot. So this is the connection. All because the string is ideal, because the string does not stretch. You don't have to go through all this reasoning. You just memorize the connection,
Okay.
which is the equation number 1, 2, 3, 4, I guess. So this is it. So the reasoning only helps us to remember this equation if you forget it. But it's not important for you. It's not important for anyone because this equation is on the equation sheet. So the reasoning is just a kind of psychological support. But in the end, this is all we need to know. That the acceleration of the weight attached to a string is related to angular acceleration of the disk, like this.
Okay. So then you would just plug
the rest of the algebra,
alpha times radius into the equation and solve.
Yes, the rest is the algebra. So t over, no, I want to multiply by -1 and divide by mass to get A only. That's going to be G minus tension over mass. And what can I do? I can do this. A over R gives alpha. So alpha is G over R minus T over MR. Doesn't have to be this way, but now what I can do is take this whole expression and put it in here. And actually, A alpha, and this is this. How? What was it? So we'll get tension times the radius equal to 1/2 mass radius squared times this alpha, which is G over R minus tension over MR. Now, a student made a mistake solving this equation, and another student made a mistake using wrong mass. As this big M represents the mass of a disk, but this little m represents the mass of a weight. So they are different.
Okay.
And now the only variable unknown in this equation is tension. So you can rearrange. Probably it could have been done differently. For example, tension could be used from here in this equation, and alpha could be replaced from this. Well, alpha equals A over R would be replaced here. Still, you would get tension on two sides in the same kind of manner. So it doesn't really matter how would you do it.
Okay. Thank you.
Sure. And well, do you have more questions? Or someone else can ask? I see more students.
I have another question, but if someone else has a question, they can go first.
Doesn't matter to me. Who's faster?
I have a question on one of the homework practice problems. It's number 9.
Number 9. There is a little note which says that you should skip problems on elastic collision because I didn't cover it. Well, I kind of told. So if it's elastic collision, you can just skip it. If it's not, oh, this one. Okay, so what's the question?
Yeah, I was just having trouble drawing like the free body diagrams and like distinguishing the different angles between the force of gravity and the displacement vector.
That's it, I understand. I don't see any ramps here, just two strings. Is it the right problem?
Yes. Yeah, it's that problem.
Why can't I scale it? Oh. Alright, doesn't matter. Okay, so what do we have? I just want a picture. How many forces does your diagram show for the object on the left?
I have tension going upward.
Yes.
Acceleration going down. The force of gravity going down.
M2 is greater than M1, right?
Yes, I believe so.
Yes. No.
Oh, no, sorry. It's
M2 is a half of M1. So if M2 is only a half of M1, how would this move in real life if you let them move? If you release them from rest?
So M1 would be going down.
Yes, M2 would be going up. That would have been the velocity. Plus, it would be traveling faster with some acceleration, faster and faster. That means acceleration also points up.
Okay.
And technically, we could apply Newton's second law, but we are told to use law of conservation of mechanical energy. Well, this is initial height for object number 2. This is the final height for the object number 2. And if I want to write what is happening to the energy, technically I should use work kinetic energy theorem. This is only for this weight, only for this mass. So kinetic initial is 0, kinetic final equals mv2 squared over 2. We can choose 0 at this level. Initial height is 0. The final height is wherever it is, h2. And change in the kinetic energy should be equal to net work. Why do I want to use kinetic energy? Well, tension does work, right, on this object. It makes it move faster and faster. So net work has two terms. The work done by gravity and the work done by tension. But these are easy terms. So mv squared over 2 minus initial equals, what is work done by gravity equal to? Well, mg y initial minus y final. What is work done by tension equal to? That's a constant force. So magnitude of a force times magnitude of displacement times cosine of the angle between force and displacement. So mv2 squared over 2 equals mg, well, 0 h, because it moves higher and higher and higher. Gravity does the negative work, but tension does positive work. Tension, distance, and this is 1. Cosine of 0. Displacement also points up. I could use this, and there is a question I remember, to calculate force of tension if I knew other things. Tension would have been equal to m2 v squared over 2 plus m2gh over L. But for that, first we need to calculate speed. So we've got another object to consider. Or, this is reasoning number 1, reasoning number 2. Also, there is a reasoning number 3 for the whole system. So let's do, well, just to see the things clearer. Gravity, tension. This is a different tension, but it has the same magnitude as tension number 2 on the left. What? Well, so this moves down faster and faster. And now what can I say again? Speed squared mass initial indicator, which is 0, will be equal to m1 g. Now, if this travels L meters up, this travels how many meters down?
It also travels
Also
L,
travels
yeah.
L meters down, exactly. So if this is y1 initial and this is y1 final, L is just the difference between these two. That's what we have here, initial height minus final height, which is L, plus, well, now tension actually does a negative work. As the displacement points down, the angle between force and displacement is 180. Cosine of 180 is -1, but still same magnitude, same distance traveled, only angle is different. Well, and now we can do it for the system. And I can do it differently. First, I can look at these two equations, 1 and 2. This is for the first, well, for one object on the left. This is for another on the right. How do I get to the system? I can add them up all together. The equation number 1 plus the equation number 2. What does it give? Squared. No, kinetic energy initial for both should be equal to what? Well, what happens to work done by tension? It disappears, getting cancelled. Because it's TL times 1, and this is TL times -1. And what do we see here? Well, see, we basically see here the law of conservation of mechanical energy, law of conservation of mechanical energy, with no friction, kinetic initial plus potential initial equals kinetic final plus potential final. We could have used this equation in the first place if we don't need to calculate the force of tension. That's actually the only equation we need. Now, what I'm missing here? I'm missing one important statement. Again, because they travel same distance in same time, they must have same speed and same, well, magnitude of acceleration. So this speed v2 and this speed v1, it's the same speed v. And now you can use this equation, the law of conservation of mechanical energy, to calculate speed immediately. And then, if you know the speed, you can use this equation, for example, to calculate the tension. Of course, to calculate tension, you also could have used Newton's second law. You would get the same result. Any question?
No, that clears it up. Thank you.
All right, thank you. In that case, next question, please.
I was wondering, this isn't like about a specific problem, but if we could go through how to solve, like when you have a like a board or something on, and then two scales and like putting a weight on it and like the process for that, if that makes sense.
Yes. So doesn't have to be scales, could be any two supports holding a board with an extra object on the top of it. Yes?
Mm-hmm.
Where do you want this third object?
Maybe like on top of one of the blocks.
Okay, left or right?
Left.
Okay. So, well, just for the sake of being as general as possible, let's make it a little bit longer. So in general, in a case like that, we would usually know the mass of this weight, the mass of the board, the length of the board, and this distance. And this distance, I don't know. So this describes the whole situation. So we can pick a number if you want to. 1 kilogram, 500 grams, 1.5 meters, 30 centimeters, 70 centimeters. Numbers do not matter for strategy, but it just makes us feel better that we know things, right?
Yeah.
All right. Strategy. So this is not a diagram yet, it's just a picture. What do we need to do to convert it into a diagram?
Draw the forces.
So please tell me. Each force has a specific point of application So, for example, the force of gravity acting on the board by itself, where should I apply it?
In the center of the board.
Right here. And how should I point it?
Down.
Absolutely. All right. What about the force acting from the support on the right?
You would point it upwards.
Yeah, normally we call it a normal force number 2. And here we've got the normal force number 1. Are we done with forces?
No, you have to do the force of the weight.
Exactly. So, and it equals to the force of gravity acting on the weight. All right. So what's the next step?
You can write the torque balance equation.
Not yet.
So, assign the axis of rotation.
Yes, you have to choose. You have to do this step. So make this step. So select the location for the axis of rotation. It's your choice. Where do you want it?
Maybe at the where the weight is.
At the left support. Yes or no?
Yeah.
All right. Yeah. That's a good choice. Well, actually, before writing the equation, we need to write each torque. Torque number 1, torque number 2, 3, etc., as many forces. So the torque due to normal force number 1, the torque due to normal force number 2, the torque due to force of gravity acting on the whole board, the torque due to the force acting from the weight. And for each torque, by definition, each torque, well, relative to this axis, could be positive or negative, and should be equal to a product of magnitude of a force times, well, technically a lever arm or whatever definition you use. So for each torque, you have to tell me 3 variables. Torque number 1.
0 because it's at the axis of rotation. And then that will be the same for
this is how technically we should have written it. Normal force times 0 because there is no R, 0. And that makes this torque 0 as well,
yeah.
which is good. So pick next one. Torque number 1.
So the torque of Fn2 would be positive mg times
sorry, what did you say?
70.
Sorry, positive. I agree because relative.
Oh, sorry, I was looking at the wrong one. Times the force of N2.
You see, yes, force times what? What distance should we use?
70.
Well, I used the letter S for that. 70 centimeters,
yeah.
Correct. Okay, and one more torque now.
It would be negative mg.
Why is it negative?
Because it's clockwise.
Relative to that axis, yes. And mg times what?
Would it be like half of L minus
Well, minus what? This is what you're minus
S. I'm sorry, minus like lowercase l.
Yes. So I really, I have a question to you. Looks like, sounds like you know everything. What's your question?
I don't know. Maybe it's just the algebra I'm getting confused on. So
I'm not sure. So now the step number 5 says net torque has to be equal to 0. So technically 0 plus normal 2 times S minus mg L over 2 minus L plus another 0 equals 0. And in this equation, there's only one unknown, which is normal force number 2. So mg big L over 2 minus little l over S gives you the answer. Done. And now, to calculate normal force number 1, what can we do? Well, we could use force balance equation, because normal force plus another normal force should cancel total force of gravity action on the board and the weight. And since you know normal number 2 now, you can calculate normal number 1. That's
okay, that makes sense.
Well,
thank
again, you did all the work.
you.
I was just asking questions. Thank you.
Thank you.
Next question, please. I can see some more students joined, so you can do it. Ask a question. Be the first.
Hi, Professor.
Hello.
I actually have a question about homework 1, part 1, or homework 2, part 2, question 6.
Question 6?
No, homework 1, part 6.
Homework 1? The
Yeah.
homework 1 for the first exam?
No, sorry. Homework 2, part 1, question 6.
Homework 2, part 1, question 6. A ball is dropped from rest. Okay, hits the floor and then bounces back. What do we need to calculate? Let's see. What happened here? It doesn't insert it, you know. All right, I don't want this. I just want this. Here. A ball with the mass is dropped from rest. So initial speed is 0. The mass is a given number. Different people may have different numbers. And let's convert it to kilograms immediately. So it hits the floor. When it hits the floor, it has a speed we call final speed for this particular part of the motion. But then it bounces off the floor and reaches a new height. So this is y1, that's 0, and this is, wait, I don't need this anymore. I can use the same axis, but after it bounces, this is v initial 2. If the collision is not ideal, so some part of energy might be lost due to internal friction, external friction, and this velocity may not be equal to the final velocity of the ball when it hits the ground. And probably that is the case because y2 is not equal to y1. Is that correct?
Yes, that's correct.
Okay. So you need to calculate change in magnitude. Or there's a second question, you need to calculate magnitude of change. Those are two different questions, and they have slightly different strategies, but the initial is the same. You need to know two speeds. You need to know this one, because this speed times mass gives you this momentum. Well, so far we call it final. And this speed times mass gives you this momentum. So far we call it initial. Now the problem with this problem is it has three different problems. First you have falling down, then you have collision, and then you have moving up. 1, 2, 3. And the time running ahead and ahead, time runs, doesn't stop ever. So for the first process, the initial time is set, assigned to the initial location of the ball. The final time for the process number 1 is when the ball hits the ground, but the final time of the first process is, incidentally, the initial time of the second process, which we call a collision. So this will be the initial momentum for collision. And then when collision ends, this ball starts to fly up. This momentum is the initial for the third process, but this momentum is also final for the second process, final for the collision. What do you need to calculate? Well, if you need to calculate change in the magnitude, what does it mean? It means magnitude final minus magnitude initial. That's what change is. Final for collision minus initial for collision. Well, what is magnitude of change? Well, that's the magnitude of change. Change is difference between final and initial. So that's going to be final for collision minus initial for collision. That's what you need to calculate. And of course, in this situation, we have to use components because this component will be positive and this component of momentum will be negative. That makes difference. Now what do we do? Well, speed. To calculate speed, we have to use other processes. The process number 1 tells you the speed at the bottom. You have to apply, well, don't have to. You could apply expressions for law of conservation of energy. That's what I'm going to do. Mechanical energy, or you could have used equations for motion, free fall motion with constant acceleration. So, but the energy does it faster. Initial energy is potential only. No kinetic. And when it hits the ground, there's only kinetic. No potential. And this gives the final speed for the process number 1. Sorry. For the process number 1. But the final speed for the process number 1, as we know, is initial speed for the process number 2. So the initial momentum for the process number 2 collision will be equal to mass times this speed, well, times -1, because it points down. Now, the process number 3 tells us that at the bottom, there is only kinetic energy. That's initial energy for the process number 3 and no potential. But at the top, it stops. There will be no kinetic, only potential. And that gives you that speed. It is initial for the 3rd process, but this is final for the 2nd process. This is the one we need to use as the final momentum for the collision by multiplying mass and this speed. It's positive because it points up. And at this point, you're just multiplying everything. You're calculating these numbers, and then you use these numbers in correct way here, here, and you need to finish this on your own.
Okay, thank you.
You're welcome.
Professor, could you also explain what, like, magnitude of the change in the ball's momentum versus change in the magnitude of the ball's momentum? Like, the wording of that was also a bit confusing.
I don't know. What else are you looking for? If it tells you, calculate, determine the following: magnitude of the change, and then B, change in the magnitude. You could calculate something else, but that wouldn't be what WebAssign wants you.
Okay. Thank you.
Sure. Who's next? Or next question, or next person.
Hi, Mr. Lee. I had a question on part 3.
Part 3 problem number?
Question number 2.
Question number 2, this one.
Yeah, it's actually, I kind of have like a more specific question on it.
Okay.
I can ask it.
Yeah, go ahead.
So I'm having trouble on part B specifically, and I wrote out, like, I'm using like A, C, and E, like law of conservation of mechanical energy. So I'm using.
So you did the part A.
Yeah, I did part A already.
All right.
And
I can explain what's happening with part B because I know from experience the wording is not very clear. However, actually, I've explained this problem in my previous hours, so there's a video for that.
Okay.
So this is what picture shows you, but what it asks you about the part which is not in the picture. The train begins its motion above, and then travels faster and faster and faster and faster, and then enters the loop and gets to the loop. Right here, this train travels horizontally in that direction. And what you are looking for is how much higher, not how high, because in a class, this is what we found. In a class, we have found the height of this object above the ground. That's not what you're looking for in part B. In part B, you're looking for how much higher your train was above the top point of the loop. This is your unknown for the part B. See?
Yes, yeah.
So in this case, you should not choose 0 on the ground. You should choose 0 here at the top. In this case, this radius will not matter on its own. The speed here, well, we can call it final, is related to this height, which is initial relative to this 0. And your equation given by the law of conservation of mechanical energy is just mgh equals mv squared over 2. Well, final. This is immediately, this gives you the answer immediately. So don't overthink it.
Okay,
This is what it is. Yeah, it says, assume the roller coaster from rest. Rest is important. So no kinetic energy. And this is how much higher above the top of the loop in order to travel through. All right. What does it mean? It means that now this speed should have critical value. Not the value you've been calculating in part A.
I see. I originally did that. I assumed that it would be the critical speed, so then I substituted G times R for B.
Yeah.
And I ended up getting the incorrect answer, but I was looking through Piazza and I assumed that someone else had asked this question. And I think maybe R is supposed to be the velocity in A. I'm not sure because I was getting hung up on that because
I'm not sure either actually what this question wants us to find. It's not clear, it's ambiguous. So in this case, we can make two natural assumptions. Natural assumption number 1, this speed is critical speed. Natural assumption number 2, this speed is the speed from part A.
Okay.
One of these will give the correct answer. That's it.
Yeah.
We've got 6 trials, so you can miss 1 or 2.
Okay, got it. Okay. Thank you.
Yes. Actually, I don't know. I don't remember. Someone should solve it and post it on Piazza. Someone should help other students and say, in this problem part B, speed should be.
Yeah, I think the comment on Piazza was actually saying that the speed we should be using is the speed found in part A. Then I gave that a go and I still got it wrong, but I might have messed something else up, so I'm gonna try it again.
Okay.
Thanks, man.
Sure. Okay, next question, please. I can see some more students still in the meeting, so please just ask the question. You don't have to be nice to other people. You have to be polite. That's required by law. But you don't have to be nice. There is no law that requires people to be nice. So jump ahead and ask a question. No?
Professor,
Yes?
we go over our homework to part 4, question 3.
Part 4. Question 3. All right. Actually, this is what I want to do. Come on. First of all, there is no picture here, so we have to draw the picture, and that is related to how we read it. So uniform by a hinge. So there's a wall, there's a hinge, there's a rod. Horizontal cord, string, rope. So the string has to be horizontal. So now the rod has to be attached to it like this. That's the only way to do it. And you know the mass, you know the length, the angle 33 degrees above the horizontal. So this is actually theta, which means this is theta. Well, we don't need this. It all gets determined automatically if we do it right. What is the first step? This is a picture, not a diagram yet. So what do we have to do to convert it into a diagram?
You have to add in the forces.
And how many forces?
Well, there'd be one tension force from the string towards the wall, a force of gravity in the middle of the rod,
Absolutely.
mg. Then there would be a force of friction acting up on the hinge.
From the hinge.
Sorry, from the hinge.
Yes.
And
I don't know how to call them normal and call it friction. Doesn't matter. We could call them 1 and 2. Technically, those are just components of an actual force acting from the hinge on the rod. That's it. 4 forces, pretty good. What's the next step?
next step would be to assign a axis
And where do you want it?
at the hinge.
That's what I would do as well. And now, so the torque because of friction is 0 because no distance. Torque for the normal is 0. that's why this choice is convenient. So now, torque due to tension, positive or negative relative to this choice of the axis?
It would be counterclockwise, so positive.
Counterclockwise, positive, correct. And it has to be equal to product of magnitude of the force times?
Times the distance, the radius, so that would be just the rod length. Oh no, it would be the lever arm. Yeah.
You have to make your mind.
It would be the lever arm.
Exactly. If you write this, this will be wrong. This is not the lever arm. This is distance from this point O to this point, I don't know, B. That's what L is. L is from O to B. Well, we've got actually 3 different expressions for magnitude of torque. So you could continue, and that would be magnitude of force times magnitude of a distance between point of application of a force B to the axis of rotation times what?
Times the distance?
No, I think that is why this might be confusing. So this is wrong. But if you say the lever arm, first of all, you have to use a different letter. Lever arm usually something like this. And that's the lever arm for force of tension. That will be correct now, but still not very informative because you don't know the lever arm. But
Could you use the theta?
If you do it right, of course. If you do it wrong, no. So you cannot use theta yet because you do not see lever arm. It's not in your picture. It's not a part of any triangle. How can you use any triangle, any theta, if you don't see that variable in a triangle? So where is lever arm?
The lever arm is an extension of the line of application, so the T would just go extend in both directions.
That I don't understand. Line of action is the extension of the vector of a force. That is correct, but that is not lever arm. That's the line of action. This blue dotted line is the line of action of the force of tension. What is the definition of the lever arm?
It's perpendicular to the axis.
Exactly. So now you can tell me if you use this notation from geometry, OB or AB or BC or wherever, you can tell me the lever arm.
Would it be C?
The lever arm is the distance from one point to another point. So you have to say 2 points.
From the axis to C.
From O to C, OC.
Yeah.
That is correct. That is correct. This is what the lever arm is. And now, only now, you can see it. And now, only now, you can say something about it, how it is related to an angle and something else. So how can you calculate the lever arm now if you apply a triangle?
You would do sine of 33 equals x over 2.3.
Well, sine of theta equals I don't know what x is.
Oh, sorry, lever arm.
Lever arm over the whole length L.
Okay.
That is correct. And from this equation, you can calculate the lever arm and plug it in the torque. And that would give you actually the expression number 2 that we used to use after the definition. The definition was, remember, magnitude of torque equals the y component times distance, then this, and this is the expression number 3 magnitude of force times lever arm. So this is what we're using here, but the lever arm comes from geometry. Done with torque of tension. Done. So how about the torque due to force of gravity acting on this rod? Is it positive or negative?
Clockwise, so it would be negative.
Absolutely. Clockwise. Now, of course, the magnitude of the force, and now we need the lever arm for force of gravity. And now, what you have to do is draw a better picture, because this picture is confusing. It has too many elements now. So you have to draw big, that's the middle point, big picture. That's mg, that's the axis, that's the angle, that's another angle. And now, again, you have to repeat the procedure for a lever arm. What do we do first?
Extend the mg.
Yes, we need to extend it to see the line of action. What do we do now?
From the axis, draw perpendicular to that.
Yes, because the lever arm is the shortest distance from the axis of rotation to the line of action. This is the lever arm for mg. And, well, do you see any triangle you could use?
Yeah, because you know the length of the hypotenuse is half of 2.3.
Absolutely. This is this. So the lever arm now will be related to cosine. All right. So now torque balance equation says net torque equals 0. So what was it? It was positive tension L times sine theta minus, because it's negative, gravity, a half of length times cosine theta equals 0. So this is the torque number 1 for the tension equals force of tension times length times sine of theta.
Okay.
And I didn't write it. This is the torque number 2. It's negative. It equals to magnitude of a force times the lever arm, which is a half of the length times cosine theta. And torque of tension plus torque of gravity equals 0. And this is it. This is your equation.
Yep.
You can notice that the length actually in this case doesn't matter. Tension times sine will be equal to mg over 2 times cosine. Or tension will be equal to, well, I can do some geometry, 2 over tangent. I think that's it.
Okay, thank you.
Ah, no, we didn't finish. Now we need to calculate components. Normal, well, yeah, components, vertical and horizontal. All right, new picture. This is what we call vertical component. Hinge vertical, hinge horizontal. This is gravity. This is tension. And now we don't need torque. It's much easier using force balance equation. Basically, you've got only gravity pointing down and only vertical component pointing up, so they must cancel each other. This is basically Newton's second law relative to y-axis. And horizontally, you've got only tension and only horizontal component. This is Newton's second law relative to x-axis. Done. These are your answers.
Okay, thank you.
You're welcome. And we still have time, do we? No, we don't. So this is the last problem for today, but some teaching fellow begins office hours right now, so you can rejoin.
Okay, thank you, Professor.
Thank you very much. All right, everybody, have a nice day.
Mm-hmm.
All right, I gotta save this.